The cosmos seems chaotic, but what if every star and galaxy follows a secret blueprint? We are about to journey through 30 of the most profound theories of physics, each one a key designed to unlock the universe's hidden structures. You will gain a new understanding of reality itself, from the fabric of spacetime to the possibility that we live in a cosmic hologram. This exploration will challenge your most basic assumptions about existence. How can a black hole hold the key to our three-dimensional world? What does it mean if time itself is just an illusion? By the end, you will see the universe not as a random collection of objects, but as a complex architecture built from principles we are only beginning to grasp. What single mystery of the cosmos most captivates your imagination? Our universe began not with a slow unfurling, but with a burst of unimaginable speed. This is the theory of cosmic inflation, a concept proposing that a fraction of a second after the Big Bang, the fabric of spacetime itself expanded faster than the speed of light. In less time than it takes to blink, a subatomic speck of reality was stretched to a size larger than our entire observable universe. This incredible growth spurt solves two of cosmology's greatest puzzles. It explains why the universe appears so uniform in every direction we look, and why the geometry of space is so remarkably flat. The evidence for this event is etched into the oldest light we can see, the cosmic microwave background. This faint afterglow from the infant universe shows a nearly perfect temperature across the entire sky, a hallmark of this rapid smoothing and stretching. But what was the engine for this explosive beginning? Physicists point to a hypothetical energy field called the inflaton field. Think of it like a strange, cosmic landscape where the early universe was perched high on a hill. As it rolled down this hill of potential energy, that energy was converted into the frantic expansion of space and the creation of all the matter we see today. This leads to an even more staggering possibility: eternal inflation. The process may not have stopped everywhere. While inflation ended in our pocket of the cosmos, creating our bubble of a universe, it could still be happening in other regions. This suggests our entire reality might be just one bubble in a frothing, endless multiverse, a sea of inflating space where new universes are constantly budding off into existence. This single theory not only sets the stage for every galaxy and star we see, but it opens a door to realities beyond our own. This initial burst of inflation set the stage, but what is the stage itself made of? We descend from the cosmic scale to the very smallest possible level, where the rules of our everyday world break down. Here we find the second great theory, string theory. It proposes a breathtakingly elegant idea. The fundamental building blocks of the universe are not tiny, solid dots, but unimaginably small, vibrating loops of energy called strings. Think of the strings on a violin. A single string can vibrate in many different ways, producing a unique note from a low C to a high G. In string theory, each distinct vibration of these cosmic strings corresponds to a different fundamental particle. One specific resonance creates an electron, another creates a quark, and yet another produces the photon, the particle of light. In this framework, every particle and every force in nature, from gravity to electromagnetism, is just a different melody played on these tiny, vibrating strings. This elegant idea, however, comes with a profound requirement. For the mathematics of these vibrations to be consistent, the strings cannot exist in merely the three spatial dimensions we know. They require more space to move. String theory demands the existence of extra dimensions, often 6 or 7 more, curled up into shapes so incredibly tiny that they are hidden from our perception. These are not dimensions you could travel through. They are complex, twisted geometries at the heart of every point in space, like the intricate folds in a crumpled piece of paper too small to see. This leads to one of string theory's most debated consequences, the landscape problem. the theory does not predict one single universe with our specific laws of physics. Instead, the mathematics suggests a staggering number of possible solutions, perhaps 10 to the 500 different ways for these extra dimensions to curl up. Each configuration results in a universe with different physical constants, different particles, and different forces. Our universe, with its perfect balance for life, might be just one possibility in a vast cosmic landscape of failed physics. This transforms the question of why our universe is the way it is. It may not be that the laws were finely tuned, but rather that we simply exist in one of the rare bubbles where the strings vibrated in just the right way to allow for our existence. But if vibrating strings form the foundation of reality, the next theory suggests the universe we perceive is a grand illusion. The holographic principle proposes a radical idea that our seemingly solid three-dimensional world is nothing more than a projection. It is a cosmic hologram, its information encoded on a distant two-dimensional surface. Just like the security hologram on your credit card appears three-dimensional, but is actually created from data on a flat, two-dimensional film, our entire universe of stars, planets, and people might be a magnificent projection from the boundary of space. This astonishing concept did not emerge from pure speculation, but from the deep physics of black holes. When matter falls into a black hole, it seems to vanish forever, violating a fundamental law of physics which states that information can never be truly destroyed. The brilliant physicist Jacob Bekenstein discovered a profound clue. He realized that the maximum amount of information or entropy a black hole can contain is not proportional to its volume as you might expect. Instead, it is directly proportional to the surface area of its event horizon. The event horizon is the black hole's point of no return, a two-dimensional spherical shell. This means all the information about every star, every planet, and every atom that ever fell into the black hole is somehow stored or encoded on its two-dimensional surface. Our three-dimensional experience of the black hole's interior, its volume, emerges from the information painted on its boundary. The holographic principle boldly applies this logic to the entire cosmos. Our observable universe, with its vast three-dimensional volume, could be a projection from a two-dimensional shell that lies at the farthest edge of everything we can see. Every event, every particle collision, and every thought you have would then be a translation of information processed on that remote surface. This completely upends our understanding of spacetime. Concepts like distance and locality, the idea that objects can only be influenced by their immediate surroundings, may not be fundamental. They could be emergent properties, a useful illusion that arises from the complex way this underlying information is processed and decoded. If this is true, then the very fabric of space and time is not the bedrock of reality, but a secondary, approximate structure. We are living inside the universe's most complex simulation, a holographic display of such incredible fidelity that we mistake it for the real thing. This leads to a startling question about the nature of our own perceptions. While the holographic principle reimagines our reality as a projection, another theory asks a more fundamental question. What if spacetime itself is not smooth and continuous, but is actually made of tiny, indivisible pieces? This is the core idea of loop quantum gravity, a powerful rival to string theory in the quest to unite gravity with quantum mechanics. Where string theory proposes tiny vibrating strings, loop quantum gravity suggests that the very fabric of space and time is woven from a network of finite, interconnected loops. Imagine a magnificent cosmic tapestry. To our eyes, the fabric appears perfectly smooth and unbroken. But if you could look with an impossibly powerful magnifying glass, you would see the individual threads, the fundamental weave that gives the tapestry its structure. Loop quantum gravity proposes that spacetime is exactly like this. It is not a featureless background, but a dynamic web of these one-dimensional loops, often called a spin network. This network defines the geometry of space itself at the smallest possible scale, a scale so tiny it is known as the Planck length. This granular nature of space leads to one of the theory's most profound implications. In Einstein's general relativity, gravity is the curvature of a smooth, continuous spacetime. This works perfectly until you reach a point of infinite density, like the center of a black hole or the moment of the Big Bang itself. These points, called singularities, are where the laws of physics break down. But in loop quantum gravity, space cannot be compressed into an infinitely small point because it is made of finite, discrete grains. There is a smallest possible unit of space, just as a digital image is made of individual pixels. This means the terrifying singularity at the beginning of our universe never actually occurred. Instead of a Big Bang from a point of infinite density, loop quantum gravity describes a big bounce. Our expanding universe could have been born from the collapse of a previous cosmic phase. As that earlier universe contracted under its own gravity, it would have reached a maximum density set by the granular structure of spacetime and then rebounded, exploding outward into the universe we observe today. This transforms the Big Bang from a definitive beginning of everything into a transition, a cosmic turning point in an possibly eternal cycle of expansion and contraction. This elegant solution removes the most troubling infinities from our cosmic story, suggesting that the universe may have no true beginning and no ultimate end, only an endless dynamic dance of spacetime itself. The idea of a granular spacetime leads to a cosmos of breathtaking scope. If our universe emerged from a bounce rather than a single bang, could it be part of a much larger, perhaps infinite, reality? This brings us to the fifth profound theory, the level 1 multiverse. It is the simplest form of a multiverse and a direct consequence of the cosmic inflation we discussed earlier. If the inflationary field drove space to expand relentlessly, and if that expansion truly has no end, then the entirety of space must be infinite. In an infinite and mostly uniform cosmos, something remarkable must happen. Every single possible arrangement of matter within any finite volume must be repeated, not just once but an infinite number of times. Consider the universe you see around you. Your observable universe is a sphere extending about 93 billion light-years across, containing all the stars, galaxies, and planets we can possibly see. In an infinite space, there are regions so far beyond our horizon that their light will never reach us. And in some of those regions, the random quantum fluctuations that seeded all structure played out in an identical pattern to our own. This means there is a distant patch of space, an island universe, that is an exact copy of everything we know, a perfect duplicate of our Milky Way galaxy, our solar system, and our Earth, with a copy of you reading this very script. There are not just a few of these duplicates. In a truly infinite universe, there are an infinite number of them. Every possible variation of your life that could exist within the laws of physics is playing out somewhere. This theory offers a staggering answer to one of science's deepest questions. Why do the fundamental constants of nature seem so perfectly fine-tuned for life? The force of gravity, the strength of the nuclear force, the mass of an electron, these values appear to be set with incredible precision. If they were even slightly different, atoms would not form, stars would not shine, and life could never arise. From the perspective of the level 1 multiverse, there is no fine-tuning at all. In an infinite reality, every possible combination of physical constants exists in some vast, disconnected domain. We simply find ourselves in one of the rare bubbles where the numbers happen to be just right for galaxies, planets, and eventually us to exist. We are not the purpose of the cosmos, but merely a possible outcome within an endless cosmic tapestry where everything that can happen does happen an infinite number of times. This cosmic duplication is only the first level of a much deeper reality. Beyond the infinite expanse of our own physical laws lies a second, even more radical tier of the multiverse. Here, the very rules of the game are different. The Level 2 multiverse emerges directly from the theory of eternal inflation, the idea that the explosive expansion of spacetime never truly stopped everywhere. Picture the greater cosmos as a vast, bubbling cauldron of space, constantly boiling and expanding at speeds beyond comprehension. Within this frenzied medium, pockets of the inflationary field occasionally decay, losing their energy and settling into a stable state. Each of these pockets stops inflating and becomes its own separate bubble universe, forever isolated from all the others within the ever-expanding background. The critical point is this: when a bubble universe forms, the way it settles down is a random quantum process. The fundamental fields that dictate the laws of physics can fall into different stable configurations, like a ball landing in one of many valleys on a complex landscape. This means each bubble universe can crystallize with its own unique set of physical constants. In one bubble, the force of gravity might be 1,000 times stronger, making stars burn out in a cosmic blink. In another, the nuclear forces could be too weak to bind protons and neutrons, leaving that universe a forever sea of hydrogen gas. Some bubbles might even have a different number of spatial dimensions. Where we have 3 dimensions of space, another bubble could have 4 or 5, or perhaps only 2. This is not science fiction, but a direct and profound prediction of our best models for how the cosmos began. Our entire observable universe, with all its hundreds of billions of galaxies, is just one single bubble within this infinite froth. The diversity of the cosmos is not just in the arrangement of matter, but in the very laws of physics themselves. Our universe is not special. It is simply one possible outcome among an infinite number of other realities where the laws of nature are utterly alien. This transforms our search for a single, elegant theory of everything. We may not be looking for the one set of laws that governs all of reality, but rather for the underlying meta-laws that dictate the vast landscape of possible physics and explain why our particular bubble has the properties it does. Yet another layer of the multiverse unfolds not in the vastness of space, but in the heart of every single quantum event. This is the Level 3 multiverse, known as the many worlds interpretation of quantum mechanics. It proposes a reality so fluid and proliferating that it challenges our deepest intuitions about existence itself. In the strange world of quantum particles, an electron is not in one place at a time. Until we measure it, it exists in a blurred state of all possible positions, a superposition. The traditional view, the Copenhagen interpretation, says this cloud of possibilities collapses into a single reality only when observed. But the many worlds interpretation offers a breathtakingly different answer. It states that the superposition never collapses. Instead, the entire universe splits at that precise moment. In one new branch, you find the electron in one location, and in another, completely separate branch, you find it in a different spot. The act of measurement is not a collapse, but a branching point for reality. This is not just about particles. Every time a quantum event occurs, which is constantly, the cosmos undergoes a split. Every possible outcome mandated by quantum physics is realized in its own newly created universe. This provides an elegant solution to the infamous measurement problem, removing the need for a mysterious observer to force reality into being. The implications for identity and probability are staggering. In one branch of reality, a quantum fluctuation causes a radioactive atom to decay, triggering a catastrophe. In another branch, that same atom remains stable and history proceeds peacefully. This means there is a version of you for every possible quantum outcome that ever affected your life. A version who took a different turn on the way to work, a version who said yes instead of no, a version who, in this very moment, is hearing a completely different conclusion to this sentence. Probability itself loses its familiar meaning. When you flip a coin, you are not waiting to see a 50% chance resolve. You are about to partake in a cosmic division. Both outcomes are 100% real, each for a different version of you that now inhabits a separate, non-communicating reality. The universe we experience is not the entire story, but merely one thread in an infinite and ever-growing tapestry of parallel worlds, all equally valid, all unfolding from the same quantum source code. These branching quantum worlds and alien physics bubbles are all contained within a single, greater reality. But what if all of these realities are themselves just a tiny subset of an ultimate, all-encompassing ensemble? This brings us to the final and most profound tier of the multiverse, the mathematical universe hypothesis. It proposes a radical and humbling idea that our physical universe is not just described by mathematics, it is mathematics. More precisely, our cosmos is one specific mathematical structure, and every other logically consistent mathematical structure exists as a physical reality in its own right. Think of the whole of mathematics as a vast, timeless library. In this library, there are books containing the rules for Euclidean geometry, others detailing the complex patterns of prime numbers, and still others describing the bizarre algebras of higher dimensions. Each of these self-consistent systems is a volume in the library. Our universe, with its specific laws of general relativity and quantum field theory, is simply one of these books. We are not the authors of the story, we are characters living inside its pages. The laws of physics we work so hard to discover are not laws that were written or programmed. They are simply the inherent, unchanging properties of the particular mathematical structure we call home. Why is the speed of light constant? Why do electrons have a specific charge? These are not arbitrary settings, but necessary truths within our structure, just as the ratio of a circle's circumference to its diameter is always pi. This leads to the hypothesis's most staggering conclusion. If our mathematical structure exists as a physical reality, then so must all the others. Every universe that can be defined by a consistent set of mathematical rules must exist somewhere in this ultimate level 4 multiverse. This includes worlds governed by the simple axioms of arithmetic, realities with 10,000 spatial dimensions, and cosmoses where time runs backward or in loops. Some structures would be barren, containing nothing but a single number. Others would be infinitely complex, teeming with forms of life and consciousness we cannot even conceive. Our existence within this particular mathematical structure, one that allows for stars, planets, and conscious observers, is therefore no longer a mystery. In a reality where everything that can exist does exist, we were bound to find ourselves in a universe capable of supporting us. This idea pushes the Copernican principle to its absolute limit, suggesting that not only is our planet not special, and our galaxy not special, and our universe not special, but our entire set of physical laws is just one mundane entry in an infinite catalogue of mathematical existence. The grand quest for a theory of everything then transforms. We are not searching for the unique equation that conjured our universe into being. We are merely trying to identify which entry in the timeless library of mathematics we happen to inhabit. This elegant unification of 5 separate string theories points toward a single, more fundamental framework. M-theory is the name given to this grander vision, a theory that operates not in 10 dimensions but in 11. The 5 seemingly distinct string theories are not competitors, they are merely different faces of this single, underlying structure. Each one represents a valid description of reality, but only under specific, limiting conditions. Think of M-theory as the ocean itself, vast and deep. The 5 string theories are like different surface phenomena, waves, ripples, and currents. They appear different, but they are all manifestations of the same immense body of water. This 11-dimensional framework introduces a new and crucial player into the cosmic architecture, the membrane, or brain for short. Brains are not one-dimensional strings. They can be objects of any number of spatial dimensions. A 0 brain is a point, a 1 brain is a string, a 2 brain is a membrane like a sheet, and a three-brain has the three spatial dimensions we are familiar with. Our entire observable universe could be one such three-brain, a vast floating island in a higher dimensional space known as the bulk. All the matter we know and love, every star, planet, and person, could be fundamentally trapped on this brain like dust mites living their entire lives within the fabric of a bedsheet, completely unaware of the spacious room around them. This leads to a breathtaking possibility that directly reshapes our understanding of gravity's weakness. Gravity, unlike the other forces, may not be confined to our brain. It could be the only force that permeates the full volume of the higher dimensional bulk. If gravity's influence is spread out across these extra dimensions, it would appear vastly diluted from our perspective, trapped on our three-brain. This could explain why gravity is so astronomically weaker than electromagnetism or the nuclear forces. The force that holds you to the ground is not weak at all. It is merely leaking away from our dimensional island into the wider cosmos. This brain world scenario transforms our universe from a solitary expanse into a single page in a multidimensional book, a reality that sets the stage for even more profound cosmic connections. This concept of a brain world transforms our universe into a single slice of a much grander, multidimensional reality. Within this framework, our entire cosmos, with all its galaxies and stars, could be a three-dimensional island, a three-brain, adrift in a higher dimensional space called the bulk. All the particles that make up our bodies and our world, like electrons and quarks, might be fundamentally trapped on this brain, unable to venture into the higher dimensions. This explains why we only directly experience three dimensions of space, but gravity is different. It may be the only fundamental force that is not confined to our brain. Gravity, in this view, is the cosmic force that can leak away from our island and propagate through the full volume of the bulk. Imagine you are living on the surface of a vast taut sheet. You can slide objects around the sheet, but they never leave the surface. Now picture a source of heat placed on that sheet. The warmth radiates out in all directions, not just along the sheet, but also into the three-dimensional room above and below it. Gravity could be like that heat, dissipating its influence into the extra dimensions. From our perspective, trapped on the brain, this leakage makes gravity appear astronomically weaker than the other forces. The force that holds entire galaxies together feels incredibly feeble on a human scale because most of its strength is bleeding into a space we cannot perceive. This elegant idea directly tackles one of physics' most stubborn puzzles, the hierarchy problem. Why is gravity so unbelievably weak compared to the other forces? The electromagnetic force between two electrons is stronger than their gravitational attraction by a factor of 1 followed by 42 zeros. This is not just a small difference, it is a chasm of inexplicable proportion. The Randall-Sundrum model provides a powerful answer using the geometry of warped space. Proposed by physicists Lisa Randall and Ramon Sundrum, this model suggests that the higher dimensional bulk is not a flat, featureless expanse. Instead, it is profoundly warped, curved by gravity in a specific way. Picture our brain universe as one of two parallel walls at the ends of a short but intensely warped fifth dimension. The warping is so extreme that most physical processes are effectively locked to our brain. However, the particles that mediate gravity, known as gravitons, would have their wave functions peaked at the other brain, the hidden wall. From our perspective, this warping creates an exponential suppression of gravity's strength. It is as if gravity's true power is being diluted across a vast distance, even though the extra dimension itself could be incredibly small. This warping provides a natural and elegant explanation for gravity's apparent feebleness without invoking enormous, undetectable dimensions. One of the most startling predictions of some brain world models is the potential to create microscopic black holes in the world's most powerful particle accelerators. If these extra dimensions exist and are of a certain size, the collision of particles at incredibly high energies could concentrate enough gravity in a tiny volume to warp space into a black hole right here on Earth. These would not be the planet-consuming monsters of science fiction. They would be vanishingly small entities predicted to evaporate almost instantly into a shower of particles due to Hawking radiation. Their fleeting creation would be the ultimate experimental proof that we are indeed living on a brane within a higher dimensional reality, offering us a direct glimpse into the secret architecture of the cosmos. This elegant idea of hidden dimensions seeks to bring gravity into the quantum fold, but another profound theory aims to unify all the forces of nature under a single, beautiful symmetry. Supersymmetry proposes a fundamental partnership at the heart of reality, a kind of cosmic mirroring where every known particle has a hidden, heavier twin. For every matter particle, like an electron or a quark, there should be a force-carrying superpartner. For every force particle, like a photon or a gluon, there should be a matter-based superpartner. These twins are distinguished by a quantum property known as spin. Matter particles have a half-integer spin, a kind of intrinsic angular momentum, while force carriers have a whole integer spin. Supersymmetry flips this, giving matter particles force-like twins and force particles matter-like twins. This symmetry is so powerful that it would neatly solve two of the most stubborn puzzles in modern physics. The first is the hierarchy problem, which questions why the Higgs boson is so relatively lightweight. The Higgs field gives other particles their mass, but quantum fluctuations should drive its own mass to an astronomically high scale, making the universe uninhabitable. Supersymmetry provides a stunning cancellation. The quantum contributions from known particles, which would push the Higgs mass sky high, are perfectly counterbalanced by the contributions from their superpartners. It is a cosmic balancing act of immense precision. The second great problem supersymmetry addresses is the mystery of dark matter. The lightest of these superpartners, often called the neutralino, would be stable, electrically neutral, and only interact through gravity and the weak nuclear force. These are precisely the properties required for a dark matter particle, the invisible cosmic glue that holds galaxies together. For decades, physicists hope to find direct evidence for these superpartners. The primary hunting ground has been the Large Hadron Collider, where protons are smashed together at nearly the speed of light. The idea is that if enough energy is concentrated in one place, it could conjure these heavy superpartners into existence. An electron superpartner, the selectron, or a quark superpartner, the squark, would leave a distinct signature in the detectors, yet so far the collider has found nothing. The elegant symmetry remains unbroken in the mathematics but stubbornly absent from our experiments. This non-discovery carries profound implications. If supersymmetry is a true property of nature, the energy scale at which it manifests must be far higher than we initially hoped. The perfect cancellation that protects the Higgs mass becomes far less natural, requiring an uncomfortable degree of fine-tuning. The continued silence from the collider forces us to confront a difficult possibility. The universe may not be as symmetric as we had dreamed, and the elegant solutions we sought might lie in a different, more complex direction entirely. Supersymmetry searches for a hidden mirror to our world, but another theory proposes our entire cosmos was born from a shattering impact in a higher dimension. The ekpyrotic universe model suggests our Big Bang was not a singular point of creation, but the aftermath of a colossal collision between two three-dimensional worlds or branes floating in a higher dimensional bulk. Picture two immense parallel sheets of reality separated by a tiny gap. These branes are not entirely static. They can move, oscillating gently in the void. Over trillions of years, they are drawn together by the faint gravitational pull between them. When they finally meet, the collision is not a destructive crash of matter, but a transfer of an immense amount of kinetic energy into the fabric of the branes themselves. This energy ignites the hot, dense state we now call the Big Bang. In this view, the universe did not begin from nothing but was reborn from a pre-existing state. This leads to a compelling cyclic model of the cosmos. After the collision, our brain explodes outward, expanding and cooling for billions of years, forming galaxies, stars, and planets. But eventually, the expansion slows, halts, and a long, slow contraction begins. The universe does not collapse into a singularity, however. Guided by dark energy and the forces within the bulk, the brain gently contracts, smoothing itself out, erasing the structures of the old cosmos and preparing for the next great collision. The cycle then repeats, a potentially eternal rhythm of creation and destruction without a true beginning or end. This model offers a dramatic alternative to the traditional Big Bang singularity. Where the standard model confronts an inexplicable point of infinite density, the ekpyrotic scenario provides a well-defined physical event, a collision that can be described with known physics. It naturally accounts for the uniformity and flatness of our universe, as the slow contraction before the bang acts like a cosmic iron, smoothing out any wrinkles and preparing a pristine slate for the next cycle. The search for evidence for this breathtaking idea turns to the oldest light in the sky. Proponents of the theory suggest that the specific pattern of polarization in the cosmic microwave background, the faint afterglow of the Big Bang, could bear the imprint of primordial gravitational waves generated by that ancient brain collision. Finding a particular swirl in that polarization could be a fossilized echo of the moment our universe was struck into existence, a signature not of a beginning from nothing, but of a rebirth from a previous cosmic age. While some theories add extra dimensions, another approach dramatically simplifies the building blocks of reality. Causal dynamical triangulations, or CDT, proposes that the smooth, continuous spacetime of Einstein's universe is an illusion, emerging from a chaotic, primordial soup of tiny, geometric pieces. Imagine you are trying to build a perfectly smooth, curved surface like the shell of a geodesic dome. You do not start with a curved sheet, you start with many small, flat triangles. By connecting these simple, rigid triangles according to specific rules, a larger, curved structure naturally appears. CDT applies this same logic to the fabric of the cosmos. It models spacetime itself as a vast collection of these fundamental triangular building blocks, each representing a tiny, indivisible chunk of reality. These chunks are not floating in a pre-existing space, they are space. The connections between them define its geometry, and their collective assembly creates the stage upon which the universe plays out. The critical word in the theory's name is causal. This is not a random pile of triangles. The rules for how they can connect are strict, ensuring that cause always precedes effect. In every valid configuration, time has a clear forward direction, preventing paradoxical loops where an event could cause itself. This causal structure is the engine that drives the entire model. When physicists run massive computer simulations using these simple rules, something remarkable happens. They start with a chaotic, foaming sea of these triangular pieces, a state often called the pre-geometric phase. In this phase, concepts like dimension and distance have no meaning. It is a fractal mess. But as the simulation progresses following the causal rules, this chaos spontaneously crystallizes. A four-dimensional spacetime emerges all on its own, complete with the three spatial dimensions and one time dimension we experience. It is a phase transition, much like water molecules randomly jostling in a liquid suddenly locking into the ordered structure of an ice crystal. This emergence of a familiar, four-dimensional world from a more fundamental, dimensionless reality is one of the theory's greatest successes. It suggests that our experience of a smooth, classical universe is a large-scale property, a collective behavior of countless microscopic elements. On the very smallest scales, spacetime may be a seething, turbulent foam, but as we zoom out, these quantum fluctuations average out to produce the serene, continuous stage we call home. This offers a profound insight. The dimensions of our universe may not be fundamental, but rather the most stable and probable outcome of a deeper, more chaotic quantum process. A black hole is nature's ultimate sinkhole, a region of space where gravity is so intense that nothing, not even light, can escape its grasp. Yet what if these cosmic traps are not just objects in our universe, but are the very seeds of universes themselves? This is the radical proposal of black hole cosmology, a theory suggesting that our entire cosmos exists within a black hole residing in a larger parent universe. The connection begins with a startling mathematical resemblance. The equations that describe the formation of a black hole from a collapsing star bear an uncanny likeness to the equations that describe our expanding universe running in reverse. The moment a star collapses past its event horizon, from the perspective of someone falling in, looks mathematically identical to the Big Bang of a new, expanding spacetime. In this view, the singularity at the heart of a black hole is not a dead end, but a bridge, a cosmic birthing chamber for a new reality. This idea finds a powerful voice in string theory through the fuzzball proposal. Traditional physics tells us that a black hole's core is a point of infinite density, a place where all laws of physics break down, but string theory offers a radically different picture. It suggests that a black hole is not a crushing singularity, but a fuzzball, a dense, tangled ball of fundamental strings and brains that has expanded to fill the entire volume inside the event horizon. There is no sharp boundary or central point of infinite density, just a fuzzy, complex ball of vibrating energy. If you were to fall into such a fuzzball, you would not be torn apart by infinite forces at a singularity. Instead, you would merge with the fuzzball itself, your information becoming a part of its intricate structure, resolving the famous black hole information paradox. This redefinition of a black hole's interior completely transforms our origin story. The Big Bang could have been the moment our own cosmic fuzzball began its expansion from a highly dense but not infinitely dense state. Our universe is not expanding into a void, but rather we are living within the dynamic interior of a black hole, an interior that is itself a vast, expanding universe. This leads to a breathtaking possibility for the ultimate fate of our cosmos. If our universe is inside a black hole, then every black hole that forms within our own cosmos could itself contain an entire new universe budding off from our own. Reality becomes a fractal, an infinite nesting doll of universes within black holes within still larger universes. The cosmic web of galaxies we see could be just one layer in an unimaginably vast, self-generating multiverse, where every gravitational collapse is not an end but a new beginning. The universe may be a cosmic nesting doll of black holes, but another theory suggests the entire structure is running on a different kind of engine altogether, a computer. The simulation hypothesis argues that our reality is not base reality, but an artificial construct, a sophisticated simulation created by a vastly advanced civilization. The core of this idea, popularized by philosopher Nick Bostrom, rests on a logical trilemma. He proposes that at least one of three propositions must be true. First, almost all civilizations at our level of development go extinct before achieving the technological maturity to create realistic simulations. Second, any civilization that does reach that advanced stage has zero interest in running simulations of its own ancestral past. Or third, we are almost certainly living in a simulation. If you find the first two propositions unlikely, that most intelligent life survives and that at least some advanced beings would be curious enough to run ancestor simulations, then the third option becomes a startling probability. The scientific basis for this idea is not as far-fetched as it seems. We are already creating increasingly complex virtual worlds, from detailed climate models to immersive video games populated by characters with simulated lives. The trend towards digitalization is undeniable. If this technological progression continues for thousands or millions of years, a post-human civilization could possess computing power so immense that running a vast number of highly detailed simulations, each with sentient inhabitants who believe their world is real, would be trivial. The very mathematical nature of our physical laws also lends a strange credence to this idea. The universe operates on a set of consistent, computable rules, much like the source code of a grand program. So how could we ever know if we are living in a simulation? Physicists have proposed searching for potential glitches in the matrix, fundamental limits or anomalies in the fabric of reality that might reveal its digital underpinnings. One key area of investigation involves high-energy cosmic rays. These are particles from deep space that travel at nearly the speed of light, carrying immense energy. In any simulation, there must be a finite resolution, a smallest possible unit of space and time, just like the pixels on a screen. When a cosmic ray particle with ultra-high energy interacts with this fundamental grid, it might produce secondary particles in patterns that deviate from our standard physical predictions. It would be like a glitch where the simulation struggles to render an event that pushes against its maximum processing capacity. Finding such a consistent anomaly would be profound evidence that we are not experiencing base reality, but a constructed one, a thought that forever alters our place in the cosmic order. The universe appears perfectly tailored for our existence, but this might be the greatest selection bias of all. This is the anthropic principle, a logical argument that addresses the eerie fine-tuning of the cosmos. The fundamental constants, from the strength of gravity to the mass of an electron, seem set within a razor-thin margin that allows for stars, planets, and life. The weak anthropic principle offers a straightforward, almost tautological explanation. It states that the observed values of these constants must be compatible with the existence of observers, because if they were not, we would not be here to measure them. We are not seeing a universe that was designed for us. We are simply seeing the one universe out of countless possibilities, where the random dice roll produced a winning combination. It is like a lottery winner marveling at their incredible luck while ignoring the millions of other tickets that lost. Our presence as observers automatically filters the kind of universe we can possibly find ourselves in. The strong anthropic principle takes a much more provocative stance. It suggests that the universe must have properties that inevitably lead to the emergence of conscious life. This version edges into metaphysical territory, hinting that the laws of physics are not just a lucky accident, but are in some sense compelled to produce observers. This principle finds a powerful home in the vast landscape of string theory. You will recall that string theory allows for a staggering number of possible universes, each with different physical laws. The anthropic principle provides a crucial justification for this bewildering diversity. In an infinite multiverse where every possible set of constants is realized, it is no surprise that we find ourselves in one of the rare, hospitable pockets. There is no deeper reason why the cosmological constant has its specific value, other than the fact that in a universe where it was much larger, space would have ripped itself apart before galaxies could form, and in a universe where it was negative, everything would have collapsed long ago. Our universe is not special, it is simply eligible for occupancy. This shifts the goal of fundamental physics. Instead of searching for a unique, elegant reason for why the constants are what they are, we may need to accept that they are environmental, like the oxygen content in Earth's atmosphere. We do not ask why the laws of chemistry demand that our atmosphere has exactly 21% oxygen. We understand it is a contingent fact of our planet's history. Similarly, our physical constants may not be fundamental laws, but merely local bylaws in our cosmic neighborhood. The profound, and to some unsettling, implication is that the universe is not necessarily designed with us in mind. We are a possible outcome within a much vaster and largely lifeless cosmic tapestry. The relentless expansion driven by dark energy leads to a cold, empty future, but this bleak end may be the seed of a new beginning. Roger Penrose's conformal cyclic cosmology proposes an elegant and infinite cycle where the distant future of one universe becomes the Big Bang of the next. In this visionary model, our universe is just one eon in an endless sequence. As our cosmos expands forever, all matter eventually decays, black holes evaporate, and particles lose their mass, leaving behind a universe of pure, massless radiation. At this ultimate state, a profound symmetry emerges. The vast, cold, and empty spacetime of the far future becomes mathematically identical to the hot, dense, and tiny spacetime of a new Big Bang. This is possible through a process called conformal rescaling, a geometric transformation that smoothly connects the infinite scale of the future to the infinitesimal scale of a new beginning. It is like a cosmic Ouroboros, the serpent eating its own tail, where the end and the start are the same point in a grander cycle. Penrose and his collaborators have made a controversial claim for evidence supporting this radical idea. They point to unusual, circular patches in the cosmic microwave background, which they call Hawking points. These are hypothesized to be the imprints of supermassive black holes from the previous eon. In the final moments of that prior universe, as black holes evaporated via Hawking radiation, they would have released an immense burst of energy. That energy, rescaled through the conformal transition into our own eon, would appear today as faint, concentric rings of temperature variation in the ancient sky. Not everyone in the cosmology community accepts this interpretation, with some arguing these features could be statistical flukes. Yet the idea itself is profoundly compelling, suggesting that the universe has no ultimate beginning and no final end, only an eternal, cyclical rebirth where information and structure are perpetually transformed from one age to the next. This ultimate unification has been the holy grail of physics for more than a century. We have two magnificent and incredibly successful theories that describe our reality, yet they speak entirely different languages and govern opposite ends of the cosmic scale. On one hand, we have general relativity, Einstein's masterwork, which paints gravity as the elegant curvature of spacetime itself. It perfectly describes the dance of planets, the bending of light around galaxies, and the nature of black holes. On the other hand, we have quantum mechanics, which governs the bizarre, probabilistic world of the atom. It explains the other three fundamental forces, the electromagnetic force, the strong nuclear force that binds atomic nuclei, and the weak nuclear force behind radioactive decay with breathtaking precision. The problem is stark and fundamental. In the places where these two domains must meet, like at the center of a black hole or the first instant of the Big Bang, our equations break down into meaningless infinities. General relativity demands a smooth, continuous stage, while quantum mechanics reveals a chaotic, granular world. A theory of everything would be the universal translator, the single framework that seamlessly blends these two pictures into one coherent whole. It would describe the universe at its most fundamental level, from the unimaginably tiny Planck scale, where spacetime itself becomes a seething quantum foam, all the way out to the vast expanse of the cosmic horizon. The quest for this theory is a journey to answer the most basic questions. What is spacetime truly made of? What exactly happened at the moment of creation? The theories we have explored are not isolated ideas. They are the leading candidates in this grand pursuit. String theory attempts to solve the problem by replacing point-like particles with vibrating strings, naturally including gravity through a specific vibration pattern. Loop quantum gravity takes a different path, quantizing space and time themselves into a fabric of finite loops. Even the holographic principle offers a radical strategy, suggesting that the key to unifying the cosmos lies not in the volume of space, but in the information encoded on its boundary. The immense difficulty lies in testing these ideas. The energy levels required to probe the Planck scale are billions of times beyond what our most powerful particle colliders can achieve. We are like architects trying to understand the blueprint of a cathedral by only ever observing it from 1,000 miles away. we must rely on indirect clues, on the subtle fingerprints these theories might have left on the cosmos, such as in the pattern of the cosmic microwave background or the echoes of gravitational waves. The search for a theory of everything is more than a technical challenge. It is a profound human endeavor to read the universe's final, unified source code. The search for a final theory often assumes that space and time are the ultimate foundation, the immutable stage upon which the cosmic drama unfolds. But what if the stage itself is part of the performance? The theory of emergent spacetime proposes exactly this, a radical rethinking where gravity and the geometry of the cosmos are not fundamental forces, but collective phenomena that arise from something deeper. Think of temperature. If you could hold a single atom in your hand, you could not measure its temperature. Temperature is not a property of one atom. It is a collective property that emerges from the average motion of trillions upon trillions of atoms. In the same way, the smooth, continuous fabric of spacetime and the force of gravity we experience might be illusions that emerge from the interactions of countless more fundamental quantum components. These building blocks are not in space, they are what create the very notion of space through their relationships. This idea is the beating heart of several approaches we have already touched. The holographic principle, for instance, is a powerful example of emergence. Our three-dimensional reality, with its gravitational pull, emerges from the quantum information encoded on a two-dimensional boundary. The fabric of space is not the primary reality, it is a projection, a useful image generated by a deeper layer of quantum data. Another crucial ingredient is quantum entanglement, that mysterious connection where particles share a single existence regardless of distance. Physicists are now exploring the possibility that the very geometry of space is woven from these threads of entanglement. The more two quantum systems are entangled, the closer they are in space. If you could somehow sever all the entanglement between two regions, the space between them would literally tear apart. This suggests that the connectivity of our universe, the fact that you can move smoothly from your chair to the door, is fundamentally a manifestation of an immense underlying quantum network. If this is true, then the smooth continuity of spacetime is a convincing illusion, a mirage that perfectly serves our macroscopic world but completely breaks down at the tiniest of scales. At the Planck length, a scale a billion trillion times smaller than an atom, the calm stage of Einstein's universe would dissolve into a seething, chaotic froth. Here, concepts like before and after, or here and there, would lose all meaning. There would be no definite geometry, only a fluctuating, probabilistic foam where spacetime bubbles in and out of existence. In this view, a black hole is not just an object within spacetime, but a place where the emergent fabric of reality is stretched to its absolute limit, revealing the frantic quantum activity from which it is built. Gravity, then, would not be a fundamental force, but a thermodynamic effect, much like the pressure in a gas emerges from the collective collisions of molecules. This transforms our entire quest. We are not looking for a theory of gravity, but for the theory of the quantum bits whose collective behavior gives rise to gravity and space as we know them. The universe is not built on a foundation of space and time. It is built from a network of relationships we are only beginning to decipher. Our deepest descriptions of reality are built upon two pillars we believe to be fundamental: locality and unitarity. Locality is the simple rule that objects are directly influenced only by their immediate surroundings, not by distant events. Unitarity is the principle that the total quantum probability of all possible outcomes in any interaction must always add up to 1, a guarantee that nothing is lost from the cosmic ledger. But what if these sacred principles are not the foundation of physics, but merely consequences of a deeper, more elegant geometry? This is the radical suggestion of the amplituhedron. It is not a physical object in space, but a multi-dimensional geometric shape, a jewel of pure mathematics. Its volume directly encodes the outcomes of particle collisions, specifically within a quantum field theory that describes the strong nuclear force. For decades, physicists have relied on a powerful but cumbersome tool for these calculations: Feynman diagrams. These diagrams picture particle interactions as a sequence of distinct events in spacetime, with particles traveling from one point to another, exchanging force carriers. Calculating the probability for a single outcome requires drawing every possible diagram, an explosion of complexity that can involve thousands of pages of algebra. The amplituhedron bypasses this chaos entirely. Instead of summing an infinite number of tangled paths through spacetime, you simply calculate the volume of this exquisitely defined shape. The answer you get is the same, but the process is staggeringly simpler and more beautiful. It achieves this by stripping away the two concepts that Feynman diagrams hold dear: locality and unitarity. In the geometry of the amplituhedron, particles do not interact at specific points in space and time. The notion of a definite here and now dissolves. The entire interaction is a holistic, inseparable property of the shape itself. The fact that the results obey locality and unitarity in our macroscopic world is not an input but an output, a miraculous emergent property that falls out of the geometry. This suggests that our familiar spacetime, with its clear distinctions between cause and effect, might be a blurred, approximate version of a more perfect and profound mathematical reality. The amplituhedron hints that the quantum world and the world of gravity may not be separate domains waiting to be stitched together, but are instead different shadows cast by the same geometric form. We are glimpsing a universe where the most fundamental laws are not about forces and particles moving through a pre-existing stage, but about the timeless, inherent properties of an object we are only just beginning to comprehend. Two particles separated by a galaxy can share a single existence. This phenomenon, quantum entanglement, has long defied any intuitive explanation. How can measuring one particle instantly influence its partner, seemingly bypassing the speed of light? The audacious AR equals EPR conjecture offers a geometric answer, proposing that the universe itself provides a secret shortcut. This idea connects two legendary physics papers from 1935. EPR, written by Einstein, Podolsky, and Rosen, highlighted the bizarre, spooky action at a distance inherent in quantum entanglement. By Einstein and Rosen, described a theoretical bridge through spacetime, a wormhole connecting two distant points. For decades, these concepts were seen as entirely separate, one belonging to the quantum realm and the other to general relativity. But this conjecture boldly claims they are two different descriptions of the same fundamental reality. When two particles become entangled, the theory suggests a microscopic wormhole is stitching their locations together. This is not a tunnel you could ever travel through. It is a Planck-scale bridge, unimaginably tiny and unstable, but it provides a physical geometric link that explains the instantaneous connection. The entanglement is the wormhole, and the wormhole is the entanglement. This provides a breathtakingly simple, though deeply strange, resolution to the spooky action. No information is actually traveling faster than light across the vast emptiness. Instead, the particles are essentially touching through a hidden, higher-dimensional fold in the fabric of reality. The vast distance we perceive between them is an illusion, a cosmic misdirection. This idea transforms our understanding of spacetime itself. The fabric of the universe might be woven from a vast, complex network of these tiny quantum threads. Every entanglement connection, from particles in a lab to atoms in distant stars, could be supported by an invisible architecture of Planck-scale wormholes. This would mean that the connectivity of space, the very reason you can move from one point to another, emerges from a deep, underlying web of quantum information links. It is a profound step toward unifying the worlds of the very small and the very large, suggesting that the force of gravity and the rules of quantum mechanics are not enemies, but different faces of a single geometric truth. The universe may not be built of isolated points in a void, but of an immense, interconnected network where every particle is just a node in a cosmic web of hidden tunnels. A black hole appears to be the universe's ultimate vault, locking matter away forever. But this cosmic security system threatens to shatter the very foundations of physics. The black hole information paradox presents a direct conflict between the two pillars of modern science, general relativity and quantum mechanics, with reality itself hanging in the balance. The problem begins with a simple question: what happens to the information about an object when it falls into a black hole? In our everyday world, information is never truly destroyed. If you burn a book, the information contained in its letters seems lost, but in principle, a being with perfect knowledge could collect every smoke particle and trace of heat, reverse the process, and perfectly reconstruct the book. Quantum mechanics enshrines this principle as unitarity, the rule that information must be preserved through any physical process. Yet Stephen Hawking made a startling calculation in the 1970s. He showed that black holes are not completely black. They slowly evaporate, radiating away their mass in a faint haze of particles known as Hawking radiation. This radiation, he argued, is entirely random and thermal. It carries no information about the specific objects that fell in. It is pure heat. So when the black hole finally evaporates completely, all the detailed information about every star, planet, and book that ever crossed its event horizon would be erased from the universe forever. This is information loss, a direct violation of the most sacred rule of quantum theory. The universe would have no memory, and physics as we know it would be fundamentally incomplete. This paradox forced physicists to choose: either general relativity is wrong and information can somehow escape, or quantum mechanics is wrong and information can be destroyed. Decades of debate have led to several breathtaking solutions. One of the most prominent is black hole complementarity, an idea that challenges our most basic assumptions about reality. It suggests that from the perspective of an outside observer, all the information about infalling matter is smeared across the event horizon, stored there like a hologram and slowly released in the Hawking radiation. But from the perspective of someone falling into the black hole, they pass smoothly through the horizon, noticing nothing unusual, carrying their information into the interior. Both stories are simultaneously true, yet fundamentally incompatible. An observer cannot see both truths at once. It is like the parable of the blind men and the elephant, where one feels the trunk and another the leg, each describing a completely different reality, yet both are touching the same animal. This radical proposal preserves both quantum mechanics and general relativity, but at the cost of a single, objective reality. Another, more violent solution is the firewall hypothesis. It argues that to prevent information loss, the event horizon cannot be a peaceful place. Instead, it must be a blazing wall of high-energy particles, a literal firewall that would instantly incinerate any astronaut falling through it. This firewall would protect the information by preventing any information from actually entering the black hole in the first place, but it shatters Einstein's principle of equivalence, the very cornerstone of general relativity, which states that free falling through an event horizon should feel like floating in empty space. The holographic principle, which we explored earlier, offers perhaps the most elegant way out. It posits that the information is never truly inside the black hole at all. It is always stored on the event horizon's two-dimensional surface, and the three-dimensional interior we imagine is just a complex projection of that data. When the black hole evaporates, the information on the surface is faithfully encoded into the outgoing radiation, preserving the quantum rulebook without any contradiction. Each of these solutions resolves the paradox, but at a profound cost, forcing us to abandon a deeply held intuition about space, time, or locality. The black hole information paradox is more than a technical puzzle. It is a gateway, forcing us to ask what we mean by reality, and revealing that our universe may operate on logic far stranger than we ever dreamed. This discrepancy between prediction and reality is so vast it defies all human intuition. The cosmological constant problem stands as the most embarrassing failure in the history of theoretical physics. To understand why, we must look at the quantum nature of empty space. The vacuum is not truly empty. According to quantum field theory, it is a seething, bubbling sea of virtual particles. These are particle and anti-particle pairs that constantly flicker into and out of existence, borrowing energy from the vacuum for an impossibly short time. Every cubic centimeter of space, even in the darkest, coldest void between galaxies, is alive with this frantic quantum activity. Each of these fleeting virtual particles carries a tiny bit of energy, and this collective energy of the vacuum should act as a source for gravity. It should produce a powerful repulsive force, a cosmological constant. When physicists calculate the expected strength of this force by summing up all the contributions from every possible quantum field, they arrive at a number. That number is 1 followed by 120 zeros larger than the value we actually observe from the accelerating expansion of the universe. To grasp the scale of this error, imagine predicting that a single grain of sand would weigh as much as our entire observable universe. Our prediction is that much more wrong. This is not a small rounding error. It is a catastrophic disconnect between our two most powerful theories, quantum mechanics and general relativity. The tiny positive value we do see is what we call dark energy, the force gently pushing the cosmos apart. But why is it so absurdly small, yet not quite zero? A perfect zero would be easier to explain, perhaps the result of a fundamental symmetry that cancels everything out. But this slight, non-zero value is a whisper in a cacophony, a delicate balance that allows galaxies to form and life to emerge. Solving this problem may require a revolution. Perhaps a new, undiscovered symmetry in nature cancels the immense quantum noise, leaving only this faint remnant we detect. Or, as we have seen before, the anthropic principle may provide the bleakly simple answer. In the vast landscape of a multiverse, most universes have a cosmological constant so large that space rips itself apart instantly, or so negative that it collapses immediately. We can only exist in one of the rare, freak bubbles where this value is almost, but not quite, zero, a tiny island of stability in a sea of cosmic catastrophes. The cosmological constant problem is a stark reminder of how much we have yet to learn, a glaring signpost pointing toward a deeper layer of reality we have not yet begun to fathom. Galaxies spin so fast they should tear themselves apart. The outer stars whirl at velocities that defy the gravitational pull of all the visible matter at the galactic center. Something invisible must be there, a hidden scaffold providing the extra gravity to hold everything together. We call this cosmic ghost dark matter, and its nature is one of the greatest structural mysteries in the universe. The leading candidate for this invisible substance is a hypothetical particle known as a weakly interacting massive particle, or a WIMP. As the name implies, this particle would have significant mass, but it would interact with normal matter only through gravity and the weak nuclear force, the same force responsible for radioactive decay. This would make it almost entirely transparent to light and ordinary matter, allowing vast clouds of WIMP to pass through our planet and even our bodies without a trace. For decades, physicists have built exquisitely sensitive experiments deep underground to catch one of these elusive particles. These detectors are placed in old mines or beneath mountains to shield them from cosmic rays, hoping to record the faint, rare ping of a WIMP colliding with an atomic nucleus. Yet, after years of searching, these underground laboratories have heard nothing but silence. This profound quiet has led physicists to consider a different kind of phantom particle, the action. Actions are theorized to be incredibly light, potentially billions of times lighter than an electron, but they would exist in staggering numbers throughout the cosmos, like a fine, invisible mist filling all of space. Unlike WIMP, actions would not be detected through a direct collision. Instead, scientists are building powerful magnetic fields, hoping to convert these ghostly particles into faint, detectable radio waves. The action is a compelling candidate because it was originally proposed to solve a completely different, esoteric problem in particle physics, and its existence would neatly resolve two profound puzzles at once. But what if we are searching for a particle that does not exist? A radical alternative suggests that dark matter is not a substance at all, but a sign that our understanding of gravity itself is incomplete. This idea is known as modified Newtonian dynamics, or MND. It proposes that on the vast, gentle scales of galactic rotation, the force of gravity behaves differently than Isaac Newton or Albert Einstein predicted. It becomes slightly stronger, providing the extra pull needed to keep stars from flying away without invoking any invisible matter. Think of it as a cosmic rule change where gravity's pull does not fade as quickly over immense distances. In this view, the dark matter problem is an illusion, a mirage created by our incomplete laws. While MND has had some success in predicting the rotation of certain galaxies, it struggles to explain other phenomena, such as the observed bending of light around massive galaxy clusters, which strongly suggests the presence of a hidden, massive ingredient. So the mystery deepens. Is the universe filled with a cosmic fog of unknown particles that weave galaxies together, or are we witnessing the subtle failure of our most cherished theory of gravity? The true architecture of the cosmos may be built from matter we cannot see, or governed by rules we have not yet fully written. Dark energy is the universe's most dominant force, and we have no idea what it is. This mysterious pressure, making up about 68% of the cosmos, is responsible for the accelerating expansion of space, pushing galaxies apart at an ever-increasing rate. The leading explanation is the simplest one we have, the cosmological constant. This idea, first proposed by Einstein and later discarded as his greatest blunder, suggests that empty space itself possesses a fundamental, unchanging energy density. Think of it as an inherent property of the vacuum, a constant push woven into the very fabric of reality. The cosmological constant is a steady, relentless force, its strength never wavering as the universe grows older and more diffuse. This constancy leads to a specific and rather bleak forecast for our cosmic fate, a gradual unraveling into an ever colder, darker, and emptier void. Yet for all its mathematical elegance, the cosmological constant confronts a problem of staggering magnitude. The predicted energy of the quantum vacuum is 120 orders of magnitude stronger than what we observe. This is not a small error. It is the largest discrepancy between theory and experiment in the entire history of science. This profound failure has compelled physicists to consider a more dynamic possibility, a theory called quintessence. Imagine if dark energy were not a constant feature of empty space, but a fluid and energy field that permeates all of reality and changes over time. This field could be weakening or it could be strengthening. The name quintessence comes from the ancient idea of a fifth element, a substance beyond earth, air, fire, and water that filled the heavens. In this modern version, the quintessence field would be a new fundamental component of the cosmos, one with a repulsive gravitational effect. Unlike the rigid cosmological constant, a quintessence field could evolve, interacting with itself and with matter in subtle ways. This dynamism opens up a spectrum of possible futures far more dramatic than a slow freeze. If the field weakens over time, the acceleration of the universe could eventually slow, perhaps even reversing into a catastrophic collapse, a big crunch. Conversely, if the field strengthens, it could lead to a far more violent end known as the Big Rip. In this scenario, the repulsive force of dark energy would grow without bound, overwhelming every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration intensifies, stars would be ripped from their solar systems. In the final moments, planets would be shredded, atoms would be pulled apart, and the very fabric of spacetime would be torn asunder. The ultimate fate of everything, from the largest galaxy to the smallest particle, hinges on the true nature of this dark energy. Is it a steady, eternal hum, or a changing field with its own life cycle? The answer lies in measuring the expansion history of the universe with even greater precision, tracing how the acceleration has changed over billions of years. Unlocking this secret means discovering not just what the universe is made of, but how its final chapter will be written. Our universe is meant to be isotropic, the same in every direction, a fundamental assumption of modern cosmology. Yet the oldest picture we have, the cosmic microwave background, contains strange, large-scale features that seem to defy this principle. Astronomers have nicknamed the most prominent of these the axis of evil. This is not a literal axis of darkness, but a surprising alignment. The patterns of hot and cold spots in this primordial light appear to be coordinated along a particular line stretching across the sky, an unexpected preferred direction that makes our local neighborhood of space look strangely special. This alignment seems to connect the plane of our solar system with the plane of our galaxy's orbit in the local group, a correlation that should be statistically impossible if the universe is truly random and isotropic. It is as if the universe has a faint, fossilized north and south pole, a remnant of something from before the Big Bang. This directly challenges the Copernican principle, the cornerstone idea that we do not occupy a privileged place in the cosmos. If the axis of evil is real and not a fluke, it suggests our location is somehow imprinted on the fabric of the universe, a thought that would revolutionize our entire cosmic story. Another deep mystery is the cold spot, a vast, unusually cool region in the southern galactic sky. It is so large and so cold that it is incredibly difficult to explain with our standard model of cosmology. Some scientists propose it is a cosmic supervoid, an immense emptiness where few galaxies formed, but its scale is so grand that even this explanation strains credibility. Another, more radical possibility is that the cold spot is a bruise, the imprint of a collision with another universe in the multiverse during the inflationary epoch. These anomalies force a difficult question. Are we simply seeing statistical ghosts, patterns that inevitably appear in any large dataset, like seeing faces in the clouds? Or are these the first genuine cracks in our standard model, tiny windows offering a glimpse into a far more complex and layered cosmic genesis, one where our universe's birth was not perfectly smooth, but was influenced by structures or events that came before? If the universe truly lasts forever, then the most likely observer might not be you or me. It could be a single, isolated brain that has just popped into existence from a random quantum fluctuation, complete with a full set of false memories of a past that never was. This is the Boltzmann brain paradox, a thought experiment that takes the logic of probability to a terrifying extreme. It is named for the physicist Ludwig Boltzmann, who first grappled with how ordered systems like our universe could emerge from chaos. In an infinitely old or eternally expanding cosmos, the statistical odds become bizarre. A random fluctuation that creates a fully formed, self-aware brain, complete with the sensation of sitting in a room and listening to this script, is astronomically simpler and more probable than a fluctuation that creates an entire, ordered cosmos with 14 billion years of consistent history. The sheer number of particles and the precise coordination required to make a single star, let alone a galaxy or a conscious civilization, is immense. But to spontaneously assemble a single, thinking brain in the void requires a much smaller, more likely jump in entropy. So if our cosmological models point to an eternal reality, then the number of these disembodied brains should vastly outnumber the number of real, embodied observers like us who evolved naturally within a cosmos. The paradox is this: if the theory is correct, then you are statistically almost certainly a Boltzmann brain, a momentary glitch in the void about to dissolve back into chaos, rather than a person with a real history. This presents a profound crisis for both probability and observation. Our entire scientific method is built on the assumption that our memories and records of the past are fundamentally reliable. If we cannot trust that the world existed before we opened our eyes this morning, then all of science, and indeed all of knowledge, collapses into solipsistic doubt. The universe we think we are studying would be nothing more than an elaborate, fleeting hallucination. The implications for our cosmological models are severe. Any theory that predicts an eternal universe, whether through eternal inflation or a cyclic model, must somehow explain why we do not find ourselves as these lonely phantom minds. Some physicists argue this paradox is a powerful reductio ad absurdum, a logical argument that proves our models of an eternal cosmos must be flawed or incomplete. Perhaps the universe is not eternal after all, and it will end in a way that prevents these fluctuations from ever occurring. Or perhaps there is a deeper principle of physics, a law we have not yet discovered, that forbids the formation of such complex, isolated observers. The Boltzmann brain forces us to confront the very nature of existence and observation, questioning whether the vast, ordered cosmos we see is the most probable reality, or just an incredibly lucky and temporary accident in an endless sea of chaotic noise. This relentless march of time feels like the most undeniable fact of our existence, yet physics presents us with a profound and unsettling silence. The fundamental equations that describe our cosmos, including the Wheeler-DeWitt equation of quantum gravity, contain no variable for time at all. They are static, timeless statements about the relationships between things. This is the problem of time, a chasm between our lived experience and the bedrock of physical law. How can the vibrant, flowing river of our lives emerge from a frozen mathematical landscape? Some physicists propose that time is not fundamental, but an emergent property, a collective illusion that arises from the way complex systems interact. Think of the concept of temperature. A single molecule does not have a temperature. Temperature is a property that only makes sense when you have a vast collection of molecules jostling together. In the same way, the flow of time might not exist at the most basic level of reality. It could be a story that the universe tells itself as its countless quantum components become entangled and change their relationships with one another. Our perception of a moving now, the feeling that the future is open and the past is fixed, could be a consequence of our scale and our limitations. We are macroscopic beings embedded within the system, and from our perspective, this intricate dance of quantum connections creates the irresistible arrow of time. This leads to the mind-bending concept of the wave function of the universe. In quantum mechanics, the wave function describes the probability of finding a particle in various states. The wave function of the universe would be a mathematical object that encodes the probability of every possible configuration of the entire cosmos all at once. It is a frozen snapshot of all that ever was and ever could be, with no inherent past or future. Our journey from birth to death, the entire history of galaxies, would be just a single path through this timeless mosaic. So why do we not perceive this eternal now? The answer may lie in the unique nature of our consciousness, which seems to be wired to process information sequentially, carving a linear narrative from a reality that is fundamentally whole. We are like readers who can only absorb one word of a book at a time, mistakenly believing the story is unfolding in that moment, while the entire text already exists complete and unchanging. This transforms time from a river carrying us forward into a vast, static landscape through which our awareness is simply moving. The cosmos seems perfectly tuned for life, from the strength of gravity to the mass of an electron, yet the universe remains profoundly silent. This is the Fermi paradox, the stark contradiction between the high probability of alien civilizations and our complete lack of evidence for them. With hundreds of billions of stars in our galaxy, many older than our Sun, the sky should be teeming with ships and signals. So where is everybody? One chilling answer lies in the concept of the Great Filter. This theory suggests that the evolution of life from its origin to a spacefaring civilization must include at least one stage of development that is astronomically difficult to pass. This stage acts as a silent cosmic sieve, filtering out nearly all potential life forms before they can announce their presence across the galaxy. The terrifying question is not whether this filter exists, but where it is located in the long chain of evolution. Is the Great Filter behind us something we have already miraculously overcome? This would mean that one of the steps we have already passed, like the emergence of the first self-replicating molecule, the jump from single cell to complex multicellular life, or the development of human-level intelligence, is so incredibly rare that we might be the first, or one of the very few, civilizations in our entire galactic neighborhood. Our loneliness would then be a sign of our incredible fortune, a testament to having navigated a cosmic bottleneck that leaves the universe largely sterile and silent. The alternative is far more unsettling. What if the filter is still ahead of us? This implies that the development of advanced technology inevitably leads to a self-inflicted catastrophe. Perhaps every civilization that reaches our stage soon discovers a fundamental physical truth, a hidden structure of reality that leads to its own destruction. It could be the easy creation of planet-killing weapons, the unleashing of runaway artificial intelligence, or the tragic discovery of a particle physics experiment that can destabilize the vacuum of space itself. The silence of the heavens would then be a grave warning, a collection of tombstones for civilizations that reached for the stars only to erase themselves from existence. This paradox is deeply intertwined with the universe's hidden architecture. The same fine-tuning of physical constants that allows for our existence might also contain the seeds of a future filter. The precise value of the cosmological constant, the specific strength of the nuclear forces, these are not just numbers that permit life, they are the very rules of a game that may have only one tragic end game. Are we the exception, the lucky ones who slipped through a cosmic crack, or are we simply naive, blissfully unaware of the catastrophe that awaits us just around the corner of technological maturity? Our search for alien life is therefore a race to answer the most important question in human history. Are we the universe's first great success or its next great failure? Our journey through the hidden structures of reality leads us to the final frontier, the nature of consciousness itself. The 30th theory proposes that mind is not a mere accident of biology, but a fundamental component of the cosmos as real as space and time. This idea suggests that the universe's mathematical architecture and the inner world of experience are two sides of the same coin. One compelling framework is integrated information theory, or EIT. It argues that consciousness is not about what a system is made of, but how its components are organized. Consciousness is the intrinsic ability of a system to influence itself, to have a cause and effect power over its own state. The more integrated and differentiated this internal network is, the higher its level of consciousness, or phi. Think of a photodiode, a simple light sensor. It can be in one of two states, on or off, with very little internal integration. Its phi is nearly zero. Now picture the human brain with its 86 billion neurons woven into an impossibly complex web of feedback loops. Its phi is enormous. This theory provides a scientific measure for a seemingly mystical quality, suggesting that even non-biological systems could, in principle, possess some degree of consciousness if their wiring is complex and unified enough. A different yet equally profound perspective is panpsychism. This ancient idea, now gaining traction in modern philosophy, posits that consciousness is a universal and fundamental property. Just as electrons have charge and mass, they might also possess an infinitesimal spark of subjective experience, a raw feeling. Of course, an electron does not think or reason. Its experience would be unimaginably simple, perhaps a bare sensation of existence. But when these fundamental conscious units are organized in the right way, like in the intricate structure of a brain, their micro-experiences could combine to form the rich, unified stream of awareness we all recognize. This view elegantly avoids the hard problem of consciousness, the mystery of how objective, physical processes in the brain give rise to subjective feelings like the color red or the taste of chocolate. If consciousness is already there in the bedrock of reality, it does not need to emerge, it only needs to be organized. This brings us back to the quantum world and the role of the observer. The famous measurement problem in quantum mechanics asks why particles exist in blurred superpositions until observed, when they then snap into a definite state. This has led some to speculate that consciousness itself is the agent that collapses the wave function, that the hidden structure of the mind is what gives definite form to the hidden structure of the cosmos. Could it be that the universe requires a witness to bring it into full being? These theories weave the observer back into the fabric of reality, suggesting that the ultimate hidden structure we are trying to decode may not be out there in the distant galaxies, but right here in the silent, luminous space of our own awareness. The cosmos may not just be a place where consciousness occasionally appears, but a process that is, at its heart, deeply conscious. From the illusion of time to the potential for a conscious cosmos, we have journeyed across 30 breathtaking visions of reality. Each theory, from cosmic inflation to the holographic principle, is a testament to human curiosity, a bold attempt to read the invisible blueprints of existence. Together, they do not offer a single, simple answer, but they paint a magnificent and unified picture, a cosmos of infinite depth and staggering complexity that is far stranger and more wonderful than we ever could have imagined from our tiny vantage point. This grand quest to understand the universe's hidden structures is more than a scientific endeavor. It is one of humanity's greatest and most beautiful adventures, a story we are all a part of. The greatest mystery remains unsolved, waiting for the next curious mind to add a new piece to the puzzle. Tell us in the comments which of these theories most reshaped your view of reality. If you are hungry for more journeys to the edge of understanding, subscribe for more deep dives into the mysteries of the cosmos. And always, no matter what, never stop looking up at the stars and wondering what secrets they hold.